Welcome to Suchithra statistics classes. Today we are going to discuss centered limit theorem, especially Lindberg Levy theorem. So let us have a look on what is meant by centered limit theorem. Centered limit theorem, that is CLT, is name of a series of theorems. All the theorem says that the sum of large number of variables is approximately normally distributed under specified conditions. So one theorem is differ from other theorem in this specified conditions. And altogether they are telling that sum of the large number of variables is approximately normally distributed. Because of this specified conditions, we have different theorems, but we have to study only Lindberg Levy theorem in this identically distributed cases only. Or we can again say CLT is a generic name of a series of theorems which asserts that the sum of large number of random variables after standardization have approximately the standard normal distribution. These two are same. Here we are stating that it is normally distributed, and here we are telling it follows standard normal distribution after standardizing the random variable. That is, so we are going to standardize the sum of large number of random variables using its mean and standard deviation. Again, we know that function of a random variable is another random variable. So, sum of random variables is also another random variable. Then what is meant by standardization? Just a quick review. Standardization of a random variable means that is we are subtracting mean from the random variable and dividing that difference by its standard deviation. Again, from the basic statistics we can say changing the origin and scale of the random variable. Here it is to its mean and standard deviation. Therefore, we can say standardization as z equal to x minus e of x divided by standard deviation of x, where x is the random variable, e of x is the mean of the random variable, sd of x is the standard deviation of the random variable, and z notation for standard normal variable. So, in centered limit theorem, we are thinking about the behavior of sum of large number of variables. Whatever be the nature of a single random variable, the sum of large number of random variable is approximately normally distributed under specified conditions. So that's why this centered limit theorem have very good importance in statistics. We know that under the name centered limit theorem, we have a series of theorems, and each theorem differ one another regard to the assumption on random variables. All the theorems stays the same. Sum of the random variable follows a normal pattern as n tends to infinity. But the difference is in the assumption on random variables. Here we are going to study IID case of Lindberg Levy theorem. The statement of Lindberg Levy form of central limit theorem is like this. If x1, x2, etc., xn are independent and identically distributed random variables with e of xi equal to mu and variance of xi equal to sigma square for all I varies from 1 to n. Then sum Sn equal to x1 plus x2 etc. xn is asymptotically normal with mean n mu and variance n sigma square. That is, Zn equal to Sn minus n mu divided by root n sigma follows n01 as n tends to infinity. So in Lindberg Levy form, we have n independent and identically distributed random variable. So all the random variables are independent and identically distributed. So random variables came from same distribution. With E of xi equal to mu and variance of xi equal to sigma square for all I varies from 1 to n. So all the random variables have same mean and same variance and they are x's also. So we can treat these things as the condition of Lindberg Levy form. So let us read the conditions once more. Condition for Lindberg Levy form of CLTs are: variables are independent, the variables follow the same distribution, the mean and variance exists and same for all the variables. Some corollaries to central limit theorem. X bar minus mu by sigma by root n follows n01 asymptotically. So from this result we can write x bar follows a normal distribution with mean mu and variance sigma square by n. And we know that x bar is Sn by n. So Sn by n follows a normal distribution with mean mu and variance sigma square by n. Therefore Sn follows another normal distribution with mean n mu and variance n sigma square. And from this one we can say Sn minus n mu divided by root n sigma follows n01. All these things are asymptotically, that is for large n. According to central limit theorem, if n greater than 25, it is said to be large. If n less than 25, it is said to be small. In some texts, n greater than or equal to 30 is said to be large and n less than 30 is said to be small. Now let us do this problem. It is required to take a sample from a population with mean mu and variance sigma square. Use central limit theorem to determine how large this sample should be in order that probability of mode x bar minus mu less than or equal to sigma by 10 greater than or equal to 0.99. We are going to use central limit theorem. So let us think about the things what we know from central limit theorem with respect to this statement. From the results of central limit theorem, we know that x bar minus mu by sigma by root n follows a normal distribution with a mean 0 and standard deviation 1 or follows a standard normal distribution. And we know that we can write x bar minus mu by sigma by root n as z. From the area property of a standard normal distribution, we can say that P of mod z less than or equal to 2.58 is equal to 0.99. What is the meaning of this statement? 99% of area is covered in between minus 2.58 to plus 2.58. This is minus 2.58 and this is plus 2.58. And similarly, P of mod z less than or equal to 2.326 covers 0.98 area. That here we can write 2.326 326. So because of this mode sign we can write minus 2.326 to plus 2.326. It would be somewhere here. The area inside it will be 98% or alpha is 0.98. Here alpha is 0.99 or it covers 99% of area of a standard normal curve. Similarly, we can say P of mod Z less than or equal to 1.96 is equal to 0.95. P of mod Z less than or equal to 1.645 is equal to 0.90. For convenience, let us by heart these four results. They are P of mod Z less than or equal to 2.58 is equal to 0.99. P of mod Z less than or equal to 2.326 is equal to 0.98. P of mod Z less than or equal to 1.96 is equal to 0.95. P of mod Z less than or equal to 1.645 is equal to 0.90. This is from the area property of a standard normal curve. So let us write P of mod Z less than or equal to 2.58 is equal to 0.99. This is from the area property of standard normal. So let us elaborate this. Instead of Z, let us write this expression. So we have P of mod x bar minus mu pi sigma by root 10 less than or equal to 2.58 is equal to 0.99. Then let us again rewrite this. P of mod x bar minus mu. Take this sigma by root 10 to this side. Less than or equal to 2.58 into. When we are taking this one, sigma by root 10 is equal to 0.99. Comparing the question statement as well as this statement, we can rewrite sigma by 10 is equal to 2.58 into sigma by root 10 for satisfying this condition, which gives root 10 is equal to 25.8. Therefore, n is equal to 25.8 whole square, which is 666.64. Here we have greater than or equal to 0.99 and here we have equal to. So what we are going to conclude is the minimum value of n is 666. It is not 665. It is 666. So we will rewrite this as minimum sample size is equal to 666. Or we can say n greater than or equal to 666. You can work out this example using the same method. The question I will read. A research worker wishes to estimate the mean of a population using a sample sufficiently large that the probability will be 0.95 that the sample mean will not differ from the true mean by more than 25% of the standard deviation. How large a sample should be taken? Can use CLT. Thank you. Thank you for listening to the class. We will do more examples in the next video.